not. So this is again example 5.8 in your textbook, so you can look at it later on in the text as well. So it says vehicles start arriving at an entrance to a national park at 5:45 a.m. and a park booth collecting entrance fees opens at 6 a.m. and process vehicles at a deterministic rate of 20 vehicles per minute. It is estimated that 20% of the arriving vehicles have priority passes that allow them to access a separate processing booth that also opens at 6 a.m., but processes vehicles at a slower deterministic rate of 15 vehicles per minute. The deterministic arrival rate of vehicles is a function of time such that lambda of t, and we typically use the symbol lambda for arrival rates, is equal to 17.2 minus 0.2t. So it's a variable rate. It's something that is changing over time. And this is what I mentioned before, that we have a deterministic rate. And deterministic rate means, oh, we can predict the next gateway with certainty. So we claim. But that doesn't mean that that rate is constant. What this problem is telling us is that that rate is a function of time. So at t equals 0, we have 17.2 vehicles per minute arriving. But at t equals 10, that rate has been reduced by 2. So it would be 15.2 vehicles per minute. So it's changing with time as you go, as the problem progresses. So where t here is in minutes after 5:45 a.m. And so the question is, we're asked to determine the average delay per vehicle for the non-priority pass vehicles and the priority pass vehicles, starting with their arrival at 5:45 a.m. until the respective queues clear, assuming that the queuing system is, it behaves DD1, meaning we have deterministic arrivals, deterministic departures, and one channel on. Okay, so this is typical of the type of problems, queuing problems, where they are pretty verbose. You have a description of a system and you have to learn how to make sense out of it. So here we have the same problem. Let me expand the screen so we have more room to write. To solve these problems, you need to think about in terms of cumulative arrivals and cumulative departures. So let me create a cumulative plot. So we're going to have time here, and we're going to have cumulative number of vehicles. And I leave it like that because it could be arrivals or departures, right? What the problem says that at 5:45 a.m., and that's going to be the start of our problem. So we're going to put time 0 there. We're going to start measuring time from that point on. Particularly because the problem gives you some hints, right? So they tell you t is in minutes after 5:45. So it's not that you have to guess too much what it will be a good origin there of the graph. Vehicles start arriving, and we will have some cumulative arrival curve. Notice that the arrival rate, if I'm interested in the cumulative arrivals, how are those going to look like? Before I go there, this problem, I don't know, I don't think it's a good problem from the point of view of to start with the subject, because it adds a complication that it's, I think it's unnecessary for the first problem you see in this type of, in this area, which is, it's telling you, oh, I have a certain arrival rate, but then I'm going to split that into two. We have priority passes and non-priority passes. So on the priority passes are 20% of the total arrivals, and the non-priority passes are the rest, 80%. Okay, so the first thing you have to figure out is how many vehicles arrive of each. So basically, this is like having two queuing problems at once. You're solving one problem for priority pass holders and a different problem for non-priority pass holders. So let's do it I did it just for the non-priority pass holders. And you can look at the priority pass holders solution in the textbook. Let me characterize what the lambdas are going to be. So I'm going to essentially, I will define the lambda, the arrival rate for non-priority pass vehicles. That will be essentially 0.8. So 80% of those guys, of the people that arrive. So 0.8 lambda will give me the arrival rate for non-priority pass vehicles. So it will be, if you multiply by this 0.8 by this, you will get 13.76 minus 0.16 t. So that's the arrival rate for non-priority pass vehicles, and obviously for priority pass vehicles it would be, and I forgot to put, it's a function of t in both cases. It will be 0.2 lambda of t, and that's equal to 3.44 minus 0.04 t. Now, knowing the rate, we can figure out what would be the cumulative arrivals as a function of time. And obviously at time zero, we are starting the problem there, we have no vehicles prior to that, so we need to start accumulating the number of vehicles that we get over time. So the cumulative arrivals is nothing more, okay, I have a rate, and let's do it for just non-priority pass vehicles. I'm not going to do it for the priority pass guys. So it would be that rate, we multiply it by an infinitesimal time, so a dt, right? And then we integrate that between 0 and some time t that we don't know. So we can do this for any time t, but for now, let me do it for t, and let me call this dt prime just to make sure that it's a dummy variable representing time. If I substitute the rate, I get the integral between 0 and t of 1376 minus 0.16 t, or t prime now, dt prime. And if I integrate that, it's a very easy integral, it's 13.76 t minus 0.08 t squared. That's our cumulative arrival rate for non-priority pass vehicles, and I can get a similar function, I have it here, but I'm not going to write it to save time, for priority pass vehicles. On the other hand, all these problems are going to involve cumulative arrivals and departures. So let's figure out the cumulative departures based on the information that we're given in the problem. We are told that vehicles start arriving at 5:45 a.m., but they don't open the gate until 6 a.m. for 50 minutes, or at 6 a.m. Until then, all the vehicles that arrived never left. Okay? The departure rate for 50 minutes is a horizontal line. The arrival rate follows a quadratic expression. Okay? And you can look at that, figure out that this thing will be something like that with this type of curvature. What happens after 50 minutes? Function, cumulative departure function, what I just said for the non-priority pass vehicles is equal to 0 vehicles for t less or equal than 50 minutes. And let's figure out what happens after that. After that, according to the problem statement, once the park opens, the vehicles are processed at a deterministic rate of 20 vehicles per minute. The cumulative departure for non-priority pass vehicles, and if you have to read carefully because for priority pass vehicles it's lower. For non-priority pass vehicles, the cumulative departure as a function of time, it's 20 vehicles per minute for every minute beyond the 15 minutes, after 15. For every additional minute beyond that point. So that's really the function that you have to write, in this case for t greater or equal than 50 minutes. And you can see this is the equation of a straight line. right? And obviously, at this point in time, it's 0, and then it will increase with a slope of 20 vehicles per minute. Let's remember what the question is. The question was to determine the average delay per vehicle for the two types of vehicles we have, priority and non-priority vehicles. Basically, what we need to do, we need to get this area here. That will give us the total delay. And we need to figure out all the number of vehicles, all the vehicles that were delayed at some point in time in this system, which is this. So you can call this N, or it would be the cumulative arrivals at a time t, where that time t is from here to there. Okay. So if we figure out those two quantities, we take the total delay, which is the area of this area, and we divide by that number. I get the average delay in the system. The other thing you may want to get is what the maximum queue length is, and we have to figure out where the maximum queue length is located, and we will look at that later on. I already have my cumulative arrivals and cumulative departures. I have the functions for that. And I told you basically where we're going. Obviously, if I want to get this area, I can very easily create a function to do that. The only problem is that, and that function would involve most likely in determining an area, or sometimes analytically, sometimes in this case, probably we'll have to integrate. And if we have to integrate or even compute in an area, I have to know this quantity or this quantity here. I need to know these values. So the first question is, how do I get that? It would be typically the same thing for most problems. The way you do that is to identify, okay, I need to get this quantity and that quantity. What defines those quantities? That quantity, we find them when these two curves intersect. That means when the Q disappears. That's what defines that point. So we have to make the cumulative arrivals, and these are the cumulative arrivals, and I'm working for the non-priority pass vehicles right now, and this would be the cumulative departures. Actually, let me do it here. This line and that line are the cumulative departures for non-priority pass vehicles. Now they left for 50 minutes, and then they start leaving at 20 vehicles per minute. So we have to make the cumulative arrivals equal to the cumulative departures. That's what defines that point. And so since I have the function, it's just a matter of writing 13.76 t minus, actually I'm going to call it, since I'm doing it for this particular time t, at which the two curves intersect, I'm going to write it with uppercase T, minus 0.08 t squared. That needs to be equal to 20 t minus 15. So you can see I'm making this equal to that. And you can see in the graph why I'm picking this line and I'm not picking that part of the graph, right? So when you do this, then you get that from there that time is equal to 33.6 minutes. And so that's an important quantity. This is one of the things that would typically be asked in problems. So now to get the total number of non-priority pass vehicles that were in a queue, we just plug that value into this expression. So we get cumulative arrivals of non-priority pass vehicles at time t is 13.76 times 33.6 minus 0.08 times 33.6 squared, and that gives me a total of 372.02. And again, you know, we don't have fractional vehicles, so that would be 372. But for intermediate calculations, usually I will use those numbers. That's how many vehicles arrive. That's typically another thing you want to compute in this type of problems. Now, remember the question was, we need to get the average delay. So the first thing we need to do is get in the area between these curves. So for that, now we can create, we can do an easy integration. Let's get the total delay. That total delay, I'm going to compute, let me go back again. I need to compute the area between this quadratic expression given by this equation here and this horizontal line and that inclined line. Use what you know about geometry. So you know that if I integrate, if I take this curve and I integrate it, can anybody tell me what would I get if I integrate this function between this times 0 and that time t? Actually, let me fix, there's something I'm realizing here, that t gets up to that point only. So all we need to do is just integrate this function between 0 and t, and then you just subtract the area of this triangle, which would be, given what we have already computed, it's really, really easy to do. Let's say I will call 1 the whole area under that quadratic expression, and 2 would be the area of that triangle. So all I want to do then, I want to make the area of 1 minus the area of 2. And the area of 1, we say, is the integral under the curve, so it will be from the integral from 0 to 33.6, or you can call it if you want, but let me just put the number 33.6. And the function was 13. Let's say 13.76. I was missing something in my notes here. 13.76 t minus 0.08 t squared dt minus the area of the triangle. And remember, the area of the triangle has a base of t and a height of n, or cumulative arrivals of t. We have both values. So one is 372.02 vehicles, and then the area. So sometimes I say stupid things, and I hope you guys start correcting me, otherwise you will, this will stay there forever. So I said, I know this is the height, but the base of the triangle is t minus 15 minutes, right? That would be times t, which is 33.6 minus 15 minutes. And since that's a triangle, it has to be divided by 2. If we do the calculations, I get 3,295.9. That depends how many decimals you carry. Vehicle minutes. That's approximately 3,296 vehicle minutes. So that's the total delay in the system. And then we can compute the average delay. Which is the question that was asked in your textbook. So the average delay is just simply the total delay. So this is for non-priority pass vehicles, divided by the cumulative arrivals for non-priority pass vehicles when the queue up to the point where the queue dissipates, which is the total number of vehicles that were delayed. So that's the values we obtain. And this would be divided by 372.02 vehicles. And obviously that cancels, and we get the average delay. And sometimes for delay, we will use W for waiting time. So let me write it like this. It would be the average delay, 8.86 minutes. Any questions so far? Is it simple enough? If I ask you to determine what's the maximum queue length in this system, what would you do? I want to hear from you guys. So what Maria is saying, let's get this high. How do I know that's the maximum Q length? Why is it there? Or, you know, and this drawing is a sketch, right? So if you plot things in a scale, perhaps you may know, but how do I know it doesn't happen here or it doesn't happen there? Yeah, you first write a function representing what you want to maximize. In this case, we want to get the Q length. So we will write an equation that gives us the Q as a function of time. And then we set the derivative equal to 0. Exactly, we will do that. So let's do this and let's do it because, you know, right now we have this is a continuous function and this is another continuous function up to this point where we have a break in this function, right? So here there's a sudden change, so there's a discontinuity in the difference. This function minus that function is one thing up to this point, and then it changes suddenly there. So let's play like we don't know anything, and let's get the Q length as a function of time in this area, and the Q length as a function of time in this other area. So in both cases, I can say that the Q as a function of time for non-periodic pulse vehicles is a difference between the cumulative arrivals minus the cumulative departures. Okay. It's that difference. So if we had a continuous function, I think it was Edward, but I'm not sure who answered the question. If I had a continuous function, I would do this, right? It would be, I would set that derivative equal to 0, and that would result in the derivative of cumulative arrivals with respect to t minus the derivative of cumulative departures with respect to t is equal to 0. And if then you recognize, well, that's actually what was given in our problem, which is the lambda, the arrival rate, which is a function of time. And this, which I'm going to move to the other side, is a departure rate as a function of time. Okay? So the condition for the maximum is when the arrival and departure rates are equal. If we're going to have a point over here where the slope of the line the slope of this line here is equal to here. If I were going to have a point there, that's where my maximum is. But I don't know if that's the case. Now, let's look at the functions. Because actually we don't need to, you know, I have taken derivatives to show you that, and I can show you what's going to happen later, but let me give you the intuition out of this. My lambda was this, right? Lambda starts positive at 0 time. Over time, it gets smaller and smaller. After 50 minutes, so lambda of NP at 50 minutes, that's still a positive value, 11.36 vehicles per minute. We start with a rate here, a slope of 1376. And over here, the slope is 1136. So we have a positive slope all along this segment. And obviously here, it's 0 all the time. So the lambda can never be equal to the mu in this first region. Okay. And so at 50 minutes, this is still 1136, right? The slope of the line, just slightly off on the right side. On the other hand, this starts, the rate is 20. So notice that this is decreasing, right? So the slope on any other point of the line over here would be smaller than 1136. This slope is decreasing, this is 20. Again, in this area, those two things, lambda and mu, can never be equal. And notice something else. The difference between lambda and mu here is 1136 minus 0, so it's 1136, which is positive, and here is 1136 minus 20, which whatever it is negative. So you see the lambda minus mu changes sign. That indicates that at the point where it's somewhere in between, if we had a continuous function, we were looking for the point where those two things are equal. When we have discontinuities, we try to find if there's a point of discontinuity where the difference between those two rates changes sign. So to answer what Marie said, she's absolutely right. In this problem, this is where the maximum is. Simply because if I look at lambda minus mu, it changes sign on both sides of this point. When you have a breakpoint, in this case, at t equal 50 minutes, but just a little bit on the left side, so I put a negative sign there, we have that lambda minus mu, and I'm going to stop writing the non-priority path because otherwise we will never finish. That lambda minus mu is 1376 minus 0.16 times 15 minus 0 because mu is 0, right? So this is lambda, and that's mu. That gives me 1136 vehicles per minute. And at t equal 15 minutes, but now on the right, so I want to put plus, just slightly beyond that point, lambda minus mu, and this is basically the same thing. You can put 15.00001, that's what I mean by to the right. But now the rate of mu, it's 20, right? So that gives me minus 864. And we have a change in sign. And that tells you, oh, here I have this location of the maximum. If these two values have had the same sign, you have to look for the maximum either in the first portion of the graph or in the second portion of the graph. And in some problems, you may have three different areas. You have to find where that maximum is. So I recommend this, the easiest thing to do to check if there's a change in the difference there. If at some point you find a change, that's what your maximum is. Otherwise, you have to find one of those segments, taking first derivative, setting the map equal to 0, and getting what the location of the maximum is. In this problem, then the location of the maximum is at this point, like what Marie said. So we're going to say that Qmax is equal to the cumulative arrivals at 50 minutes, because we have said that that's where the maximum is, minus cumulative departures at 50 minutes. And that's equal to 13.76 times 15 minus 0.08 times 15 squared. Remember, here we were talking about the rate, here we're talking about the cumulative arrivals, which is a different function, right? It's the integral of the rate. Minus 0, which was the cumulative departures, and we get that maximum Q length is equal to 188.4 vehicles, and you can make that approximately 188. Okay. So typically that would be a very common question in this type of problems, how to get the maximum Q length. And I wanted to cover this problem because that's one of the things you will face. I didn't want just to tell you, oh, the maximum is here. I want you to be clear why the maximum. You say, oh, that's where the maximum is. It's not always the case that it's at the break. Okay? So let me go to problem 5.9. This is basically what you have in your notes in the PDF that I wrote. So we have, after observing arrivals and departures at a highway toll booth over a 60-minute time period, an observer notes that the arrival and departure rates are deterministic. Instead of being uniform, they change over time according to a known function. More than uniform, I would have written constant. I think I took this is an example from your book. I would have written constant. They're not constant. They change over time according to a known function. The arrival rate is given by the function lambda of t equal to 0.2 plus 0.17t minus 0.0032 t squared. And the departure rate is given by mu of t equal 1.2 plus 0.00 t, where t is in minutes after the beginning of the observation period, and lambda of t and mu of t are in vehicles per minute. Determine the total vehicle delay at the toll booth and the longest queue, assuming DD1. So this is basically very similar to the problem we had before. It's actually even easier. We don't have the that break that we had before. In this case, we have two continuous functions. Okay, so let's try to answer this very quickly. We are given lambda of t equal to 2.2 plus 0.17t minus 0.0032 t squared, and mu of t equal to 1.2 plus 0.07 t. That's the information that we're given. And notice that to save time, I plotted very nicely now with Excel this time. The first one is a quadratic expression, has this form, and the second one, it's a straight line. So this is the arrival rate as a function of time, this is the departure rate as a function of time. And based on what we just said, when are we going to get the maximum queue length? See, this plot nicely. When you're performing a test, you will not have that luxury, so you will have to do this analytically, but the maximum queue length, you can already tell me, hey, when these two things happen to be equal, when these two rates happen to be equal, that's what the maximum is going to be. So we will come up with a value that is close to 38 minutes or something like that, just by looking at that. So obviously the queue will last longer than that, if that's where the maximum queue length is. So note that lambda of t is greater or equal than mu of t for values of t close to about 40 minutes. During that time, a queue will be growing, and it will start to dissipate once lambda of t becomes less than the mu of t. So beyond this point, on the left, the queue will be growing. On the right, the queue will be shrinking. So what we need to do is to write a function for the cumulative arrivals and another function for the cumulative departures. And we need to figure out at what point in time these two curves intersect. That's basically the same thing we did in the previous problem. We need to find those functions. And so we're going to find the cumulative arrivals, the cumulative departures, and then we're going to integrate. We're going to get the area under this curve will give me this area. And I want to subtract the area under this curve. And then I will get, that will give me the area in between the two curves. So that will give me the total delay. But the first thing we need to get is figure out this value of t. And that will also give us how many vehicles we have in there. And how do we solve for that? Mathematically was when the cumulative arrivals is equal to the cumulative departures. That's the condition to get the value of t. Okay? So let me write that down. So let me write what the cumulative variables of t are. Cumulative variables of t is basically the integral between 0 and that value of t that we don't know of what's given to us, the rate 2.2 plus 0.17t minus 0.0032 t squared dt. Okay, so that's equal to, that is the integral, so it would be 2.2t plus 0.085 t squared minus 0.0017 t cubed. It's a cubic function now. And let's write the cumulative departures, same thing. It would be an integration between 0, in this case, and t, of the rate that was given to us was 1.2 plus 0.07 t dt, and in this case I get that that's equal to 1.2 t plus 0.035 t squared. So if we make these two things equal, and I'm going to save the time, I'm not going to write, I get the following expression. If I make this equal to this other one, I get this expression, I get a cubic expression, 0.00107 t cubed minus 0.05 t squared minus t equals 0. You have to realize, hey, t is in the three terms, so I can take t as a common factor of 0.00. So this could be equal to 0 because this is equal to 0. That will give me one root of this cubic expression, but then I have a quadratic expression here that has two roots. And I want to save the time for you, it would be 61.8, that's one of the roots. And minus 15.1 means could be the other root. So obviously this makes no sense. So this is the only root that makes sense. This one is also a root, but it's telling me that something funny happens at that point, but that's not a maximum. It's another of the critical points. So that's it. That's the value of t, 61.8 minutes. That's the time at which Q dissipates. And then I can write the total delay in the system, dt, as the integral between 0 and 61.8 of the cumulative arrivals times dt minus the integral between 0 and 61.8 of the cumulative departures of the dt. And just make sure that you write these functions here, the ones for cumulative arrivals with lowercase t and the one with the cumulative departures with lowercase t. And you integrate. If you do that, and again, you have this problem in your textbook, so I'm not going to dwell to do that, we get 1,925.8 vehicle minutes. And with that, then we can get the average delay. The average delay, let me write it with the letter W. The average delay would be d of t divided by the total number of vehicles. And I haven't told you how I get this. If I plug in this value here, if I plug this value into either of these two equations, I get that n. And that n happens to be equal to 208 vehicles. And since I ran out of time, let me just finish this here. It would be 1,925.8 divided by 208. So this is vehicle minutes divided by number of vehicles, and you get that delay, average delay is 9.26 minutes. Okay, So what Marie asked is, how do I find the n? Not the n. This n is the number of vehicles that you see. These, each car that is affected here, they will suffer some delay. So the n gives me the total number of vehicles that were delayed somehow in the system. Once we find the time at which the two curves intersect, I can plug that time into either this expression or that expression. It will give me that point anyway. So it's just a matter of putting the value of we find for t in the cumulative departures or the cumulative arrivals. That's it. Okay, let's continue with example 5.9. At the end of the class the other day, I think it was Isabel who asked, how do we get the n? Let me repeat that in case it's not clear. Once we make the cumulative arrival and cumulative departure curves equal, and we find this point, we find this value of t, right? Now, if we plug that value of t either in the cumulative arrivals or the cumulative departures, we will get the total number of vehicles affected, right? Because we're looking at this point over here. So at that point, both curves are the same. So I plug the value of t in either curve, and I will get that value of n. So that was the value of n I was using here in the denominator the other. So let's continue with the rest of the problem. With the second part of the problem was the longest queue, assuming DD1. So let's solve for that. Let's forget, don't pay attention to this plot for now, this plot that I have here. I will explain that in a minute. So to determine the longest queue, we're going to write an expression for the queue length as a function of time. Q of t is equal to the cumulative arrivals minus cumulative departures, right? So this is basically saying, if you take any point in time, let's say at 20 minutes, this would be the queue length. It's the difference between how many vehicles arrived in the system and how many were able to depart. If I take 30 minutes, then this is the queue. So basically what we have here, that vertical difference is Q of t for any t. In that particular case would be for 30 minutes. So we write this, we write what we know, we just substitute the expressions we have for this. Is 2.2 t plus 0.085 t squared minus 0.00107, mistype that, minus 1.2 t plus 0.035 t squared. If you simplify that, it will be minus 0.00107 t cubed plus 0.05 t squared plus t. So that's our length of queue as a function of time. Almost always going to have a continuous function. What we may not have is a function that has continuous slope, the derivative of the function. So, but in this case, we have a continuous function and it has continuous derivatives. The derivative of q with respect to time, in this case, a very easy function. It's a quadratic function, so it's minus 0.00321 t squared plus 0.1 t plus 1. And if we make that equal to 0, the first derivative equal to 0, we find the condition for a maximum. So in this case, we get that t star is 39.12 minutes. And if we go back with this value and put it into our Q1 equation, we get that Q maximum is equal to, with me writing, so it's 51.6 vehicles. Okay, so obviously we cannot have parts of a vehicle. So in practice, for the class, just leave it like that. It makes my life easier to know what value you actually got. But in practice, you would round that value to 52 vehicles. And if you are doing a design of something that you are interested in, how many vehicles you want to store, probably you will design that for 55 or something like that. So I forgot to mention, what you see here is basically this expression of Q as a function of time between 0 and the value of t that we had before. We solved for t was 61 point something, so that's the value of t. So it starts at 0, it goes to 0, and in between it gets a maximum. Close to what I told you the other day where we got the maximum. Okay? Which is exactly what you see, the separation between those two curves, but it's just different. Okay?